this is a supplementary video for graph sketching exercises. So we have done 3 exercises in class, leaving 5 unsolved because we are currently way behind the schedule and we have to start the new topic next lecture. So I have no choice but to include the solutions in this supplementary video. Okay, so we should start with problem 28. So here the function is x divided by root of x squared plus minus 1. And this is an algebraic function. Well, as you can expect, the derivative is quite tricky, but at least we have got an expression for the derivative. So this function, so computation of these guys will be complicated. But once these derivatives are figured out, so you could see that the properties of this function is indeed much easier. Okay, let's start by determining the domain. So because x squared minus 1 is inside the square root, so it has to be greater or equals to 0. But however, since this guy is also in the denominator, it's not supposed to take 0. So to make sense of this fraction, it's necessary and sufficient for us to require that x squared minus 1 is greater than 0. So this basically says x minus 1, x plus 1 will be greater than 0. So if you look at the graph over here, so minus 1 and positive 1, this will separate the real line into 3 parts. And well, if you look at each factor, so we see that x minus 1 is positive on the right and x minus 1 is negative to the left of 1. And then x plus 1 is negative to the left and minus 1 and positive to the right over here. So this way I know that this polynomial x squared minus 1 will be positive, negative, and positive. So with this information, since we want to find out the x that makes the product to be positive, so the answer for this will be x greater than 1 or x is less than minus 1, so that the domain in the interval notation will simply minus infinity to minus 1 union 1 with 1 to infinity. All right, so this is how we determine the domain. Okay, so for the y-intercept over here, so this does not apply because the function is not defined when x equals to 0. For the x-intercept, so we see that x divided by root of x squared minus 1, this guy equals to 0. It implies that x equals to 0, but then again, this is outside of the domain. So, okay, so the conclusion is actually this function really does not intersect the x-axis. All right, so that's what we have known from here. Now let's discuss symmetry. So if you substitute x by minus x in the expression of f of x, what you will get is minus x divided by root of x squared minus 1. And this is precisely the negative of f of x. So this will tell me that I have got an odd function. So this means all I need to do is to focus on half of the domain with positive values. So this means all I need to do for the rest of the steps is to focus on the interval positive 1 to positive infinity. Okay, so this is what the symmetry can help in simplifying the discussion. Now let's study the asymptotes. So we will start from investigating the limit of the function at infinity. So as x gets large, well, I need to get the limit of this guy. Well, to get the limit of this guy, I need to divide both the numerator and the denominator by x. So the top guy is easy. X divided by x is simply 1. For the denominator, well, I'm supposed to be multiplying 1 over x. All right. So when you try to place this 1 over x into the square root, so there are some sign issues. Well, this sign issue does not really exist when x is positive, because when x is positive, so you have got x equals to absolute value of x, which means x equals to square root of x squared, so that you could directly place this 1 over x into the square root, resulting in 1 over x squared times x squared minus 1 over x squared. So, well, simplify the denominator, you get root of 1 minus 1 over x squared. Okay, as x approaches infinity, so x squared, 1 over x squared, so namely this guy, well, this guy will approach 0 from above. So what I will get is going to be 1 over square root of a number that is slightly less than 1, because 1 minus a positive number is going to be smaller than 1. So 1 divided by a number that's slightly less than 1, that will be slightly greater than 1. So that's how I can see that f of x is approaching 1 from above as x gets large. Okay. On the other hand, if you are trying to get the limit at negative infinity, so when you are trying to place this 1 over x into the square root, you keep in mind that in that case, you have got x equals to minus absolute value of x, which is minus root of x squared. So when you try to place that guy into the square root, remember that there has to be a negative sign in the front. So as a result, you will actually see that, well, the resulting limit will still be 1 divided and minus root of 1 minus x0 plus, well, the resulting number will be a little bit smaller than -1. So that will approach, well, the function will approach -1 from below if x is approaching negative infinity. Okay, so if you didn't use the symmetry to simplify the problem, then this is something that you need to know and you need to keep in mind that there is a sign issue when you're trying to place anything into the square root. But fortunately, well, the symmetry allows us to focus on 1 to infinity, so we can simply forget about all these kind of stuffs. All right, so this way I know that there is a horizontal asymptote at y equals to 1. And moreover, by symmetry, will actually leads to us that there is also another horizontal asymptote at y equals to -1. So this will be clear when you try to rotate the graph 180 degrees about the origin. So that's basic, that will be clear there. So for the vertical asymptote, we see that if x is sitting in this domain, then, well, the function value will be a finite number. So we cannot expect a vertical asymptote in this interval. However, at the end point, so you could see that, well, the function has got the denominator 0. So this hints us that we should have got a vertical asymptote at 1. Let's make it more precise, and more importantly, we need to determine whether or not it's taking positive or negative infinity. Okay, so as x approaches the 1 from the right, I don't need to discuss the left-hand limit because the function is not defined to the left of 1. Okay, as x approaches 1 from the right, my f of x being the quotient of this guy is going to be the following. So the numerator is approaching 1, and the denominator, notice that x is a little bit greater than 1, so x squared will also be a little bit greater than 1. So x squared minus 1 will be a little bit greater than 0. So root of x squared minus 1 will be a little bit greater than 0. So this tells me that I have got a quotient whose numerator is 1 and whose denominator is a very small positive number, and the answer for this guy will be positive infinity. Okay, so this way I get a vertical asymptote at x equals to 1. All right, so this concludes the discussion of asymptotes. Now let's look at the derivative. So you see that f prime of x is looking like this, and you could see that f prime of x equals to 0. This means -1 over root of x squared minus 1 equals to 0. So, but from this guy over here, you get no solution. But f prime of x does not exist. So this is possible. So this basically means x squared minus 1 equals to 0, and then you get x equals to plus or minus 1. Okay, so, well, but plus minus 1, they are out of domain. So there's really no critical numbers that ever existed. Okay, so now let's look at the increasing decreasing. Well, for this case, it's quite easy because we only have got one number. So it's really a hollow dot because the function is not defined over there. So we only have got one interval, and then let's look at the derivative. So notice that the square root in the denominator is always positive. Well, it takes 0 when x equals to 1, but then x is not supposed to take 1. So this guy is always positive. Then together with the minus sign, you can simply determine that the function will be decreasing over this interval. And besides, we know that there is no local mean or local max because we simply do not have any critical numbers in this case. Now let's analyze the concavity. I need to copy this f double prime of x to the next page. So what I have now is f double prime of x is going to be equals to 3x divided by root of the 5th power of x squared minus 1. Let me double check if that's correct. Okay, yeah, that's what I have. Okay, so you see from this expression that f double prime of x equals to 0 implies that the numerator equals to 0, so means x equals to 0. And then, but x equals to 0 again is out of domain. And moreover, f double prime of x does not exist. This means x equals to x squared minus 1 equals to 0, so then x equals to plus or minus 1, again out of domain. So this means, well, we do not really have a critical number for this problem. And if you want to analyze the concavity, so it's still going to be the same situation. We only have got a ray from 1 to infinity, and then the concavity doesn't really change over here. Okay, so you can either plug in a special value or you simply read from the expression over here. So the square root is never negative, and the x on top when x is greater than 1, so this is always positive. So that way you determine that the function is concave upward. And moreover, because there's really no critical number for the derivative of f, so we see that there's no inflection point. Now let's draw the graph. So first, the function is defined to the right of 1, and then there's no intercepts, and there's a symmetry of odd functions, so that we focus on this interval for now. And then there's actually horizontal asymptote and the vertical asymptote over here. So let's actually put these asymptotes on the graph. So this is the vertical asymptote at the number 1, and this is the horizontal asymptote at the number y equals to 1. Okay, so we know that the function is approaching positive infinity to the right of 1, and the function is approaching 1 from above, well, as x gets large. So this basically makes it possible for us to draw these 2 bits of the function. Okay, so, and there's no local max, local min, or inflection points, so there's no other special function values. So that we can directly connect these 2 pieces. So since the function is decreasing in a way that is concave upwards, so that way we can connect the graph, connect these pieces like this. All right, so this will be the graph for f of x when x is greater than 1. Okay, so once this part is clear, then all we need to do is to rotate everything by 180 degrees. So to be more precise, let's just draw the symmetric vertical asymptote at the number -1, and also we should draw the symmetric horizontal asymptote, well, at the number -1. Okay, so then the graph will simply be like this, and in a way that is symmetric about the origin. So these 2 parts are supposed to be symmetric about the origin. Okay, so this finishes number 28. Now let's look into number 30. So the function is an algebraic function. So with the fractional powers, x to the 5/3 minus 5 times x to the 2/3. So the derivatives are very easy in this case is because they are power functions. You just get the derivative directly by power rule. Now let's study the domain. So just recall one thing, that x of p over q, if q is odd, so this guy is defined everywhere if p is greater than 0. So we are going to use that. So using this part, we see that f of x is defined everywhere. So the domain for this function is going to be -infinity to positive infinity. Okay, so the y-intercept is pretty easy. You just set y equals f of 0, and the answer will be 0. For the x-intercept, you need to set f of x equals to 0. So f of x equals to x to the 5/3 minus 5 times x to the 3/2. Okay, so to handle this equation, I need to factorize a little bit. So when you are dealing with a factorization involving the fractional power, the general rule is the following. So you always factor out the smallest power of x. So in this case, the smallest power of x is going to be x to the 2/3. So I would just factor that guy out. Okay, so after factoring out x to the 2/3 power, I will get, so the first guy, I need to subtract 5/3 by 2/3, and the answer will be x. And the second guy, what remains is simply 5. Okay, so this is the factorization of f of x, and if I set this guy equals to 0, I get x equals to 0 or x equals to 5. So we have got two intercepts, x equals to 0 and x equals to 5 on the x-axis. All right, so now let's look into the symmetry. So if I plug in f of minus x, so I would get minus x to the 5/3 power minus 5 times negative x to the 2/3 power. So if negative x to the p/q, so this has got two possibilities. So the first possibility is going to be equals to xp/q itself. That in this case happens if p is even. And on the other hand, if it's going to be equals to minus x to the p/q, so this case happens when p is odd. And of course, everything of this happens assuming that q is odd. Okay, so using this fact, I can simply see that this is going to be simplified as minus x to the 5/3 minus 5x to the 2/3. Okay, so you see that this guy is neither f of x nor f of minus x. And moreover, this is obviously not the periodic function. So this way we conclude that there's no symmetry for this function. Okay, so this means we need to be considering the function behavior over all the domain. Okay, so let's investigate the asymptotes. So, we start by investigating the limit at infinity. So, to get this limit, so I will just use my factorization, f of x equals to x to 2/3, x minus 5. So that you see that as x gets large, so the first factor gets large as well as the second factor. So as a result, I know that the function gets positively large. Okay, on the other hand, if x approaches to minus infinity, so I have got the same expression of this guy over here. Okay, now you have to be a little bit careful. So because s is approaching negative infinity, so the second factor is going to be approaching minus infinity, so it will be negatively large. However, the first factor, because the numerator over here is even, so this guy is still approaching positive infinity. So what I will get is the product of one very large number together with one very negatively large number. So the answer will be negatively large. So that's how I get the limit to be minus infinity. So in particular, so there's no horizontal asymptote. Okay, so do we have vertical asymptotes? Well, because the function is defined everywhere, so we can also conclude that no vertical asymptotes. Okay, so this is the analysis of the asymptotes. Now let's get into the increasing decreasing. Well, we need to use this form of f prime of x, but to solve the critical number out of this guy, I will need to factorize it again. So again, use the same principle, always factor out the lowest power. In this case, the lowest power will be minus 1/3. So I will just factor out x to the minus 1/3. Okay, what remains inside will be 5/3 times x to the 2/3 plus 1/3, because I'm factoring out a negative power, so I need to supplement it into the power over there. Okay, so that will be the first guy, and the second guy is simply going to be 10/3. So you see that I can still factor out 5/3 in addition. And moreover, this x to the minus 1/3 power, I can move it to downstairs. So ended up in the x 1/3 power in the denominator. All right, so after this further factorization, what I get is going to be x minus 2, because if you factor out 5/3 from 10/3, what remains is going to be 2. All right, so this way I can see clearly that if f prime of x equals to 0, so this means x equals to 2, and f prime of x does not exist, implies x equals to 0. All right, so this way we get two critical numbers, and let's just plot them on the graph. So these two critical numbers separates the real line into 3 parts. And I need to analyze the increasing or decreasing by looking at the sign of the derivative. Okay, so This is not difficult because let's actually place the factors all over here. So first I have both 5/3 times x minus 2. So this is one factor, and then x to the 1/3 power, this will be another factor. Okay, so for the first factor, it will be positive to the right of 2, and to the left of 2, it will stay negative. And for the second factor, so x to the 1/3, so it will be positive to the right of 0, and it will be negative to the left of 0. Okay, so that means my function will be increasing because the derivative is positive. It will be decreasing because the derivative is negative, and it will be increasing again because the product of two negative numbers is positive. Okay, so well, this also makes the local maximum at 0 and local minimum at 2. So we need to get those two numbers. So we see that f of 0, so this is going to be 0. So this way we see that f of 0 equals to 0 is a local maximum. And moreover, f of 2, so this is going to be 2 to the 5/3 minus 5 times 2 to the 2/3. All right, so this is quite annoying. So let's actually, again, perform the factorization. So that way I will get 2 to the 2/3 times 2 minus 5. So that way I will get minus 3 times 2 to the 2/3. Okay, so this guy is a little bit smaller than 2, and this guy is going to be minus 3. So I think what I will get is going to be a number between -3 and 6. Okay, let's keep that in mind. So I will get f of 2 equals to minus 3 times 2 to the 2/3 power. So this guy is a local minimum. Okay, so that's the part E and F. And can we fit the part G in here? Probably, because as long as we can make some space by arranging this over here. Okay, let's discuss part G, the concavity. So we know the f double prime of x. Well, to handle this guy here, again need to use the factorization. And the principle is the same. I need to factor out the lowest power of x. So in this case, I should use this guy as common factor. So what I will get here is going to be x to the minus 4/3. So, well, then the first guy over here, so I need to modify the power by a positive 4/3. And for the second guy over here, this is simply going to be this guy. Okay, so simplify the expression so I can further move out the 10/9 in the front. And moreover, I can kick this negative power of 4/3 in the denominator. Okay, what remains is going to be x plus 1 in the parentheses. Okay, so then you see that f double prime equals to 0. So this means x equals to minus 1, and f double prime x does not exist. This means x equals to 0. All right, so this way I can again draw the picture of the number line. But in this case, actually, let me just move this. I will just, so 0 is to the right and minus 1 is to the left. And these two numbers separates the real line into 3 parts. Okay, so I would need to determine the sign of each factor in the second derivative. Okay, so I basically have got 2 factors, so 10/9 times x plus 1. So this is one factor, and the other factor is x to the 4/3 power. So, well, the first factor will be negative to the left of minus 1 and will be positive to the right of minus 1. And the second guy is always positive. So this way, I know my function will be concave up, and concave down. And in particular, so I know that f of minus 1. So at the point minus 1, I will get an inflection point. So let me actually mark it here. So f of minus 1. Okay, what do I get? Okay, so minus 1 to the 5/3 power. So this is going to be equals to minus 1. But minus 1 to the 2/3 power, this will be positive 1. So that means f of minus 1 will be minus 1 minus 5, and the answer will be minus 6. That way, I know that my point minus 1 minus 6. So this is an inflection point. All right, so this is basically the concavity analysis. Now we are ready to draw the graph, and notice one thing, that we have got a function value at 0 minus negative number and a negative number. So that's telling me that the majority of the behavior is happening below the x-axis. This tells me that when we are trying to arrange the coordinates, we want to emphasize what's going on with the negative numbers. So because we simply need more space below. And also because the numbers, special numbers are 0 to -1, 0, and also including this 5 over here. So, well, the graph should be a little bit more emphasized on the right-hand side of the y-axis. So that's why we would, we would draw our graph in this way. Okay. So now let me mark the special points. So x equals to 0, x equals 5 will be x-intercept, and y equals 0 will be the y-intercepts. So this means I need to mark this point and another point at probably here, let's say at 5. So this will be the locations where the curve crosses the x-axis. Okay, so we have no symmetry, we no horizontal asymptote, no vertical asymptote, but then we also know what's going on when x gets large or negatively large. So this means the function will look like this way when x gets large, and the function looks like this way when x gets negatively large. All right, so let's also look into the special values. So I have got 0, 0, 0, and 2 with the negative number, and -1 with -6. So let me actually say that plot this number on the graph. So f0 has been plotted. F of 2 is roughly here. So f of 2 will probably be some negative number that's going to be further smaller than -3, but not way too much smaller than that. Let's say this is going to be by -3 times 2 to the 2 over 3. Okay, so this takes care of this point, and finally we have -1, -6. So -1 is roughly here. And then -6, so this will be quite negative. Okay, so this means I need to move this guy a little bit around like this. All right, so these will be the points. Let me mark in. This will be the special points where the function is passing through. Okay, so let's see what's going on with each individual point. So f of 0 equals to 0, so this is local max. But however, if you look at the concavity, so it says the function is concave upwards on both sides of 0. So this means, well, at the point 0, so the function cannot look like this, because if this is local max, so then the function will be concave downward, while the function concave outward. So the only possibility is, well, the function is going to be having a cusp point at the point 0. So only this way can make the function to be concave upwards on both sides. And if you look at the derivative, you also see that this is precisely the point where the derivative does not exist. So you should expect the vertical tangent at the point 0. All right, so this tells me that the function looks like this near the point 0. And moreover, near the point 2, so you see the function is concave upwards, and moreover it's a local mean. So this means we do have got this behavior like this. So that means this local minimum is basically looking like this. Finally, we have got -1, -6. So this guy is an inflection point. So, well, this basically tells me that this will be inflection point over here. All right. So, yeah, that's basically all we need to know. And now let's actually connect these bits. And let me just revise this guy over here. So the function will be increasing from -infinity, but now because in a way, so it will be increasing from -infinity in a way that is concave upward until it hits -1. So this is basically how I'm drawing my graph to be this way. So it will be increasing from -infinity to this inflection point. After this inflection point, well, the function becomes increasing in a way that is concave upwards until it hits this cusp point at 0. So after it hits 0, the function will be decreasing in a way that is concave upward until it hits 2. After it hits 2, it becomes increasing again. So, well, moreover, throughout the process, the function is concave upward. So this basically says that I should really draw my graph in this way, and it has to pass through the number 5 on the x-axis and then move further way up. Okay, so roughly speaking, that's my graph for this function. Okay. Okay, so this is how you draw the graph for the function in exercise 40. I think it's necessary for me to mark this is, I forgot to mark that this is -1 and this is 2 and this is -6. Yes, it's necessary to keep these marks on here. Well, I'm not so sure if this is all going to be a big thing, but so for the most traditional way of drawing, you also need to mark the x-axis and y-axis like this. So I should also include this in the previous solutions. I need to mark that this is going to be x-axis and y-axis. And well, also more rigorously speaking, so you also need to actually state clearly. So the standard way of graph sketching also requires you to actually clearly what this curve means. So you see that you should really write this guy as y equals to, well, whatever function we are drawing. So x to the 4th minus ax squared plus 8. So for this graph, I have to say that what I'm drawing is y equals to x divided by, what was that again? X minus 4, x squared minus 4. And for the third graph, I need to emphasize that this is the graph for y equals to x minus 1 squared divided by x squared plus 4, x squared plus 1 actually, not 4. Okay, so for this graph, I need to say that what I'm drawing is y equals to x divided by root of x squared minus 1. And finally, for the graph we just handled, well, we need to specify that what I'm drawing now is y equals to x to the 5/3 minus 5 times x to the 2/3. I don't think we will be very demanding on this part. Indeed, in the exam paper, I think, well, the x, y coordinates together with the grids will be given. So you do not need to actually determine the scalings of these numbers all by yourself. So you will be given a grid to handle this. What I'm showing is here is simply the case when you're not given a grid and you need to have got a rough estimate about the function values at each point. Okay, so this is the solution to number 30.